Look at the walls around you. They feel solid, definitive, and permanent. You assume that the floor beneath your feet is a continuous foundation, and that the air you breathe occupies a three-dimensional volume that is exactly as it appears. You rely on the stability of matter and the predictable behavior of the particles that compose your body. But as you sit there, billions of subatomic ghosts are screaming through you at nearly the speed of light, and the vacuum you perceive as empty is actually a roiling sea of potential energy that, by all accounts of our current mathematics, should have already torn the universe apart. We have spent decades building the most complex machine in human history to probe the boundary of what is possible, only to find that the more precisely we measure the foundation of our world, the less sense it makes. The Large Hadron Collider has not just found a particle, it has uncovered a structural inconsistency in the fabric of the vacuum itself. We are now forced to confront a measurement that is internally perfect, but globally impossible. The architecture of precision. You are told that the universe is governed by laws, but it is more accurate to say it is governed by constants, numbers that do not change and cannot be explained. When you look at a bridge or a skyscraper, you recognize that its stability depends on the specific tensile strength of steel and the predictable pull of gravity. You assume the universe operates under a similar, grander engineering code. We call these codes the fundamental constants: the speed of light, the gravitational constant, the mass of an electron. These are not merely observations. They are the fixed coordinates of our existence. They are the settings on a cosmic dial that appear to have been locked into place at the moment of the Big Bang. If you were to nudge any of these values by the smallest measurable increment, the architecture of the cosmos would not simply change. It would cease to function. The discomfort begins when you realize that these numbers are arbitrary. There is no mathematical reason why light must travel at 299,792,458 meters per second, or why the strength of the electromagnetic force is exactly what it is. In our pursuit of a theory of everything, we expected to find a logical necessity for these values, a reason why they must be so. Instead, we have found that they simply are. We are living inside a structure built on a foundation of given facts that have no deeper explanation. This is the first crack in the illusion of a rational reality. We find ourselves in a universe that is precisely tuned for the existence of complex matter, yet the tuning itself appears to be an accident without a cause. At the Large Hadron Collider, the goal has always been to find the why behind the is. Physicists look for new particles or forces that would explain why the fundamental constants have the values they do. We expected to find symmetry, beautiful, overarching logic that would dictate the behavior of every particle. But as our measurements have become more precise, the expected symmetry has failed to materialize. We are measuring the world with unprecedented accuracy, only to find that the precision itself is a problem. The more we zoom in on the fundamental building blocks of your body, the more we realize that the stability you feel is an emergent property of a system that is mathematically precarious. Consider the vacuum of space. You perceive it as a void, a passive stage upon which the drama of matter unfolds. However, the architecture of precision reveals that the vacuum is a substance with its own density and energy. Our best theories predict a certain energy density for this empty space, but when we measure it, the value we observe is 10,120 times smaller than the prediction. This is not a minor rounding error. It is the largest discrepancy between theory and observation in the history of science. If the predicted value were true, the universe would have expanded so violently in its first microsecond that no two atoms would ever have met. If the value were slightly different in the other direction, the universe would have collapsed back into a singularity before the first photon could escape the primordial soup. You exist because of a cancellation of terms so precise that it defies any statistical probability. We are forced to ask if we are living in a Goldilocks universe by sheer luck, or if there is a darker, structural reason for this alignment that we are not yet equipped to see. The data coming out of CERN is now pointing toward a reality that is not natural. In physics, naturalness implies that the numbers should be roughly the same order of magnitude. What we are seeing instead is a universe that requires fine-tuning to a degree that suggests we are missing a fundamental piece of the puzzle. We are measuring the blueprints of a reality that, by all logic, should not be. Standing. The vacuum expectation. When you remove every atom from a cubic centimeter of space, you expect to find nothing. Yet the vacuum possesses a measurable pressure that refuses to stay at zero. You have been taught to think of a vacuum as an absence, a hollow stage where matter performs its various roles. In your daily life, emptiness is a lack of content. But to the sensors buried deep within the Large Hadron Collider, nothing is a physical object with its own characteristics, its own weight, and its own dangerous potential. This is the vacuum expectation value, and it represents the baseline energy of the universe. It is the floor of reality, and we have discovered that the floor is vibrating. This vibration is not a metaphor. According to the principles of quantum field theory, what you perceive as empty space is actually a field in its lowest energy state. However, because of the uncertainty principle, that energy can never truly be zero. Instead, space is a restless sea of virtual particles, constantly popping into and out of existence, borrowing energy from the void and returning it in a fraction of a second. You are currently submerged in this sea. Even in the deepest reaches of the intergalactic void, there is no such thing as empty. There is only the field, and the field is never still. The problem we face is one of weight. When physicists calculate the total energy contained in these nothingness fluctuations, the result is a number so staggering that it implies the vacuum should have a mass energy density greater than that of a neutron star. If the vacuum actually possessed the energy our math says it should, the fabric of space-time would be curled into a knot smaller than an atom. The fact that you can look out at the stars, or even see the other side of your room, proves that the vacuum's energy is somehow being suppressed or canceled out. We are measuring a nothing that is fundamentally heavier than the everything it contains. This discrepancy leads us to a realization that is difficult to process. Our existence depends on a near-perfect cancellation of massive forces. We are like people living on the surface of a frozen lake, unaware that miles of pressurized water are pushing against the ice from below. We have measured the pressure of this vacuum, and we find it to be a tiny, positive value, a value just large enough to drive the expansion of the universe, but small enough to allow galaxies to form. But there is no reason for this number to be so small. It suggests that the vacuum is not in its natural state, but is being held in a delicate, artificial-looking equilibrium. At CERN, When we smash particles together, we are momentarily exciting the vacuum, forcing it to reveal its internal structure. What we find is that the vacuum is not a static backdrop, but a dynamic participant in the laws of physics. It dictates how particles acquire mass and how forces are transmitted. If the vacuum expectation value were to shift even slightly, the basic properties of the electron would change. Atoms would fall apart. The chemistry that allows your neurons to fire would become impossible. You are a localized fluctuation in a field that is currently pretending to be empty, but whose true nature is a dense, energetic pressure that our current models cannot reconcile with the reality we see. The vacuum is not an empty container. It is a loaded spring. We are measuring the tension in that spring and finding that it is stretched to a point that defies explanation. We call this the vacuum expectation. But what we have found is that the vacuum does not meet our expectations of nothingness. It is a presence that we cannot see, yet it exerts a physical influence on every measurement we take. The more we probe the void, the more it feels as though we are not looking at an empty room, but at the surface of a deep and turbulent ocean. And we are only now beginning to realize how deep the water truly is. 3. The geometry of the small. The Large Hadron Collider was built to see the invisible, using sheer kinetic energy to peel back the skin of reality and expose the gears beneath. You often imagine the subatomic world as a smaller version of our own, tiny spheres of matter orbiting one another like miniature planets. But as we accelerate protons to 99.9999991% the speed of light and smash them together within the 27-kilometer ring beneath the Franco-Swiss border, that intuition fails. At these scales, size and shape lose their meaning. We are not looking for objects. We are looking for the geometry of interactions. We are attempting to map the coordinates of the invisible scaffolding that supports everything you have ever touched. When these particles collide, they do not simply break into smaller pieces. Instead, the kinetic energy of their movement is converted directly into mass, manifesting new particles that did not exist a moment before. This is the ultimate fulfillment of Einstein's most famous equation. But the process reveals something unsettling about the nature of space. At the moment of impact, the density of energy is so high that it mimics the conditions of the universe a billionth of a second after the Big Bang. For a fleeting instant, we are tearing a hole in the present to look at the raw state of the beginning. What we see is not a collection of things, but a complex web of fields vibrating in specific patterns. The geometry we uncover is increasingly difficult to reconcile with a three-dimensional world. In the high-energy environment of the collider, the distinctions between different forces begin to blur. We have seen the electromagnetic force and the weak nuclear force merge into a single electro-weak interaction. This suggests that the complexity you see around you, the variety of elements, the different types of radiation, the very structure of the periodic table, is merely the result of a symmetry that broke as the universe cooled. You are living in the debris of a much simpler, much more elegant geometric state that we can only glimpse through the violence of particle acceleration. However, as we push the LHC to higher luminosities, we are encountering a geometric silence. Our models predicted that at certain energy levels, we would see supersymmetry, a hidden set of partner particles that would balance the mathematical books of the universe. These particles were supposed to explain why gravity is so weak and why the Higgs boson has the mass it does. We have looked for them with the most sensitive equipment ever devised. We have combed through petabytes of collision data, looking for the telltale geometric signatures of these missing pieces. We have found nothing. This absence is not just a disappointment for theoretical physicists. It is a structural crisis for our understanding of reality. If the geometry of the small does not include these balancing factors, then the universe we inhabit is mathematically unnatural. It implies that the laws of physics are not the result of a deep, necessary logic, but are instead a series of improbable coincidences. We are peering at the gears beneath the skin of reality and finding that several of the most important teeth are missing. Yet the machine continues to turn. You must confront the possibility that the geometry of the universe is not what it appears to be. We have long assumed that space is a continuous fabric, but the measurements at CERN suggest a granularity or a hidden dimensionality that we are only beginning to sense. If the particles we detect are merely the points where higher dimensional fields intersect with our three-dimensional slice of reality, then your entire physical existence is a shadow cast by a shape you cannot see. The LHC was built to find the God particle, but what it may have actually found is the limit of human logic, a point where the geometry of the universe becomes so alien that it can no longer be translated into the language of cause and effect. 4. The weight of a shadow. At the heart of the current crisis is the Higgs boson, a particle whose mass was predicted by every model we have, but whose actual measurement has introduced a fatal instability. You are accustomed to the idea that mass is an inherent property of matter, that you weigh something simply because you exist. But physics tells a different story. You have mass only because you are swimming through an invisible, viscous field that permeates every corner of the universe. The Higgs boson is the physical manifestation of that field, the ripple in the water that proves the ocean exists. When it was finally detected in 2012, it was hailed as the final piece of the puzzle. But as the data settled, the celebration turned into a quiet, mathematical dread. The problem lies in the specific weight of this particle. In the standard model of physics, the Higgs boson is responsible for the stability of everything you see. Its mass should, by all logical accounts, be either enormous, near the so-called Planck scale, or it should be cancelled out by other particles. Instead, it occupies a strange middle ground, approximately 125 giga-electron volts. This number is not just a statistical curiosity. It is a precarious ledge. If the Higgs were significantly heavier or lighter, the universe would have either collapsed into itself or failed to produce stable atoms. We find ourselves in a reality that sits atop a needle's point, and the measurement of the Higgs mass suggests that the needle is beginning to bend. To understand the weight of this shadow, you must understand the concept of vacuum stability. The Higgs field determines the phase of the universe, much like the temperature determines whether water is liquid, solid, or gas. The current mass of the Higgs boson suggests that our universe is not in a truly stable state, but a metastable one. We are living in what is known as a false vacuum. This means that the current state of physics, the way gravity works, the way light travels, the way your body holds together, is not the final, lowest energy version of reality. It is a temporary equilibrium, a cosmic delay that has lasted for 13.8 billion years, but which has no inherent requirement to continue. When we measure the Higgs mass with the precision provided by the LHC, we see that the vacuum is perched. It is like a ball sitting in a slight depression on the side of a mountain. It is stable for now, but if it were given a sufficient nudge, or if it were to simply tunnel through the barrier due to quantum fluctuations, it would roll down to a much lower energy state at the bottom of the mountain. This is the fatal instability. If the Higgs field were to transition to this lower state, the laws of chemistry would be rewritten in an instant. The atoms in your room would cease to be atoms. The electromagnetic force would change its strength, and the very concept of matter would be erased. There is no warning for such an event. Because this transition would be a change in the fundamental fabric of space itself, the bubble of new physics would expand at the speed of light. You would not see it coming. You would simply cease to be, as the reality supporting your molecular structure dissolved. The measurement of the Higgs boson has given us the weight of our world, but in doing so, it has revealed that the world is a shadow cast on a wall that is currently crumbling. We are observing a particle that shouldn't be as light as it is, and its lightness is the only reason we are here to measure it. We are left with a measurement that is internally consistent, but globally incompatible with a permanent universe. The Higgs boson was the particle we were looking for to complete our understanding, but it has instead acted as a mirror, reflecting a fundamental fragility in the architecture of space. We have found the gear that drives the clock, but we have also found that the gear is made of glass, and it is under far more pressure than we ever imagined. The shadow has weight, and that weight is pulling the vacuum toward a point of no return. Would you like me to expand the next segment, the fine-tuning paradox, to continue this sequence? 5. The fine-tuning paradox. If the mass of this single particle were different by a fraction of a percent, the atoms in your DNA would lose their ability to bond, and the stars would never have ignited. You are a biological consequence of a mathematical tightrope walk. We call this the fine-tuning paradox, and it is the most uncomfortable realization in modern cosmology. It is the observation that the fundamental constants of nature, the numbers that define the strength of gravity, the charge of an electron, and the mass of the Higgs boson, appear to be set to the exact values required for the existence of complexity. If the strong nuclear force were only 2% stronger, diprotons would be stable, and the sun would have exhausted its fuel in a matter of seconds. If it were slightly weaker, no element heavier than hydrogen could ever have formed. You exist in a narrow window of habitability that is not just planetary, but structural. This is not a matter of a planet being at the right distance from a star. It is a matter of the universe being at the right distance from total chaos. When we use the Large Hadron Collider to measure these values, we are looking for a reason, a mechanism that explains why the universe is so hospitable. In any other system of engineering, such a precise alignment would be interpreted as design. In physics, however, we look for naturalness. We expect the values to arise from a deeper logic that makes them inevitable. But the more we look, the more we find that there is no such logic. The numbers seem to be arbitrary, yet they are perfect. This creates a crisis of probability. If you were to sit at a radio and turn 100 dials at random, the odds of hearing a clear symphony are effectively zero. Yet, as we measure the dials of the universe, we find a symphony. This suggests one of two possibilities, both of which are deeply unsettling. The first is the multiverse hypothesis, that our universe is just one of an infinite number of bubbles, each with its own random set of laws. In this scenario, you only exist in this one because it is the only one where you can exist. You are a survivor of a cosmic lottery, living in a rare pocket of stability within a vast, uninhabitable multiverse. The second possibility is even more difficult to reconcile with our current understanding of science. It is the idea that our measurements are missing a hidden layer of reality, a dark sector, or a set of higher dimensions that dictates these values. We have built our entire understanding of physics on the idea that we can observe the world and deduce its laws. But the fine-tuning paradox suggests that the most important laws are the ones we cannot see. We are like observers watching a puppet show, measuring the movements of the dolls while remaining completely ignorant of the strings and the hands that move them. At CERN, the search for new physics is essentially a search for the reason behind this fine-tuning. We have looked for supersymmetry, for extra dimensions, and for dark matter particles that could balance the scales. But as the experiments continue to yield null results, the paradox only sharpens. We are left with a universe that appears fine-tuned for life, yet offers no explanation for why. This is not a comfort. It is a mathematical haunting. It implies that the reality you experience is a statistical anomaly, a thin sliver of coherence in a reality that is overwhelmingly hostile to the existence of anything at all. Every time you take a breath, you are relying on the continued consistency of these numbers. You are assuming that the dials will not move. But we have no guarantee that. These constants are actually constant. Some observations of distant quasars suggest that the fine structure constant, the number that governs the strength of electromagnetism, may have been different in the deep past. If the laws of physics can drift, then the fine-tuning that allows you to exist is not a permanent feature of the world, but a passing weather pattern. We are measuring the architecture of a reality that is perfectly aligned, yet fundamentally groundless. Would you like me to expand the next segment, the ghost in the machine, to continue this sequence? 6. The ghost in the machine. Recent data from the LHC suggests the presence of an anomaly in how B mesons decay, a slight preference in direction that should not exist in a symmetrical universe. You assume that the laws of physics are impartial, treating matter and its various transformations with a cold, mathematical indifference. You expect that when a particle breaks apart, it does so according to established rules of probability that do not favor one flavor of matter over another without cause. But the B meson, a heavy and short-lived particle, is behaving as if it is being nudged by an invisible hand. It is decaying into electrons and muons at rates that defy the Standard Model's principle of lepton flavor universality. This is the ghost in our machines, a persistent, measurable signal that suggests our map of the subatomic world is missing a continent. This preference is not merely a statistical tremor. It is a fundamental challenge to the concept of symmetry. In the architecture of the small, we rely on the idea that the universe does not have a favorite particle. The three generations of leptons, electrons, muons, and taus, are supposed to be identical in every way except for their mass. They should interact with the fundamental forces with the exact same strength. Yet, the LHCb experiment has captured thousands of events where this equality is broken. The B mesons appear to be avoiding certain pathways and favoring others, suggesting that there is a force or a particle we have never seen that is interfering with the process. We are observing a bias in the basement of reality. If this anomaly is confirmed, it implies the existence of something called a leptoquark, or a new type of Z-prime boson, but the name is less important than the implication. The presence of such a force would mean that the vacuum is even more crowded than we suspected. It would mean that the empty space in your room is thick with ghost particles that only interact with matter under specific, high-energy conditions, yet exert a constant, subtle pressure on the behavior of every atom in your body. We are beginning to sense a hidden layer of causality, a set of gears that turn only when we aren't looking, producing effects that we have previously attributed to random chance. You must consider what it means for the universe to be asymmetrical at its core. If the fundamental forces are not universal, then the stability of matter is not a global law, but a local condition. We have long wondered why there is more matter than antimatter in the universe, why everything you see exists at all instead of having been annihilated in the first moments of creation. The ghost in the B meson may be the first clue to that original sin of physics. It suggests that the universe has a built-in lean, a structural preference that allowed matter to win the tug-of-war against nothingness. But a universe with a preference is a universe that is no longer a neutral observer of its own laws. It is a system with an agenda. The data remains quiet and clinical, appearing as peaks and troughs on a digital monitor in a control room in Geneva. But the implications are loud. If the standard model is broken, then the reality you rely on is merely a simplified version of a much more complex and perhaps more disturbing system. We are measuring a deviation that shouldn't be there, a slight tilt in the scales of existence. It is as if you were to flip a coin 1,000 times and find that it lands on its edge more often than probability allows. You would not conclude that the coin is lucky. You would conclude that the floor is slanted. We are now looking for the source of that slant. We are searching for a particle that does not want to be found, one that exists only in the margins of our most violent collisions. The ghost in the machine is a reminder that our understanding of the universe is an unfinished bridge. We have built it out into the darkness, and we are just now realizing that the pillars are resting on something we didn't account for, something that is quietly pushing back. The breakdown of symmetry. Nature is supposed to be indifferent to left and right, yet at the most fundamental level, the universe appears to have a built-in bias that mocks our sense of balance. You experience the world through a lens of symmetry. Your body is bilateral, the orbits of the planets are elliptical, and the laws of motion work the same whether you move forward or backward. This aesthetic harmony is more than just a visual preference. It is a cornerstone of our physics. We call it charge, parity, and time reversal symmetry, or CPT. For decades, we operated under the assumption that the universe was a perfect mirror, where every process has an equal and opposite reflection. But the deeper we descend into the subatomic architecture, the more we find that the mirror is shattered. This realization began with the discovery of parity violation. In the 1950s, researchers found that certain radioactive decays involve a left-handed preference. Electrons emitted during beta decay do not fly off in random directions. They preferentially align themselves against the direction of their spin. This was the first evidence that the universe distinguishes between left and right. It was as if we discovered that gravity only pulled objects down if they were spinning clockwise. This was not supposed to happen. In a rational, symmetrical world, the fundamental forces should be ambidextrous. Instead, we have found that the weak nuclear force, the force responsible for the sun's radiation and the decay of elements, is purely left-handed. At the Large Hadron Collider, this breakdown of symmetry has moved from a curiosity to a crisis. We have observed CP violation, a phenomenon where the laws of physics change when a particle is swapped with its antiparticle and mirrored. If symmetry were absolute, the Big Bang should have produced equal amounts of matter and antimatter. They would have immediately annihilated one another, leaving behind a universe filled with nothing but pure light. The fact that you exist, that there are stars, and that there is a floor beneath you, is proof that the symmetry was broken. The universe chose matter over antimatter. It chose a right over a left. We are the survivors of a cosmic glitch, a slight imperfection, the initial conditions of reality that allowed a tiny residue of matter to endure. But the measurement of this asymmetry at CERN is revealing a new problem. The amount of CP violation we observe in the standard model is not enough to explain the amount of matter we see in the universe. There is a massive, unexplained gap. It is as if we found a crime scene with a billion bodies and only a single bullet. This suggests that there are hidden forms of symmetry breaking, ghostly forces or interactions that we have yet to detect. These forces are not just historical artifacts of the Big Bang. They are active, ongoing violations of the logic we use to describe the world. You must consider the implications of living in a biased universe. If the most basic building blocks of reality have a preference, then the laws of nature are not neutral. They are skewed. This bias permeates every atom in your brain and every star in the sky. We are searching for a grand unified theory that would restore this symmetry at high energies. But the data from the LHC continues to show a universe that is stubbornly lopsided. The more we try to find the perfect mirror, the more we find that the universe is fundamentally, and perhaps intentionally, asymmetrical. This breakdown of symmetry suggests that the order we see is a temporary state. We are used to thinking of the universe as a stable, balanced system, but the data tells us we are living in the wake of a massive, ancient imbalance. We are measuring a reality that has a direction, a tilt that we cannot explain and cannot ignore. The symmetry that we find so beautiful in art and nature is, at the subatomic level, a lie. We are the products of an uneven foundation, and we are only now beginning to measure the depth of the slant. 8. The hierarchy problem. There is a massive, unexplained gap between the strength of gravity and the strength of the other forces, a hole in our logic that the LHC was supposed to fill, but only widened. You experience gravity as an absolute authority. It keeps your feet on the ground and governs the motion of galaxies. Yet, compared to the forces that hold your atoms together, gravity is staggeringly, almost comically weak. You can defeat the entire gravitational pull of planet Earth simply by picking up a paperclip with a small refrigerator magnet. The electromagnetic force of that tiny magnet is orders of magnitude stronger than the collective mass of 6 sextillion tons of rock pulling in the opposite direction. In the language of physics, this is the hierarchy problem. The realization that the fundamental forces are out of scale with one another by a factor of 1032. This gap is more than a numerical curiosity. It is a structural defect in our understanding of reality. According to our current mathematics, the Higgs field should be buffeted by the energy of the vacuum, causing its mass to skyrocket to the Planck scale. a regime of energy where gravity becomes as strong as the other forces. In such a universe, every particle would be so heavy that it would instantly collapse into a microscopic black hole. The fact that the Higgs boson is light enough to allow for the existence of atoms suggests that something is canceling out the vacuum's contribution with a precision of 32 decimal places. We are measuring a cancellation that is so perfect, it feels fraudulent. When the Large Hadron Collider reached its full operating energy, the scientific community expected to find the solution to this discrepancy. The leading theory was supersymmetry, or SUSY. It proposed that for every particle we know, there is a superpartner waiting to be discovered. These partners would provide the necessary mathematical counterweights to stabilize the Higgs mass and bridge the gap between gravity and the quantum world. We built the most sensitive detectors in history to catch a glimpse of these partners. We expected them to appear as clear signals, debris of our collisions. Instead, we have found a haunting, sterile silence. This silence is unsettling. It implies that the natural solution to the hierarchy problem does not exist. If there are no superpartners to balance the books, then the universe is unnatural. It means that the strength of gravity and the mass of the Higgs are not dictated by a beautiful symmetry, but by a fine-tuning that defies logical explanation. We are left with a reality that appears to be held together by a series of impossible coincidences. It is as if you found a pencil standing perfectly upright on its tip in the middle of a windstorm. You can measure the pencil, you can describe its position, but you cannot explain why it hasn't fallen over. The hierarchy problem suggests that our perception of the four-dimensional world is incomplete. Some theorists argue that gravity is only weak because it leaks into extra, hidden dimensions that we cannot perceive. In this model, gravity is just as strong as the other forces, but its influence is diluted across a higher dimensional bulk. The LHC has searched for the signatures of these extra dimensions, microscopic black holes or gravitons escaping our reality. But so far, the data has remained stubbornly three-dimensional. We are looking for the leak, but the room appears to be airtight, yet the pressure continues to drop. You are currently held together by forces that are vastly more powerful than the space that contains them. We are measuring a universe where the weak and the strong forces operate on one scale, while gravity operates on another, and there is no visible bridge between them. The hierarchy problem is a reminder that the standard model of physics is a description of the surface, not the foundation. We have reached the limits of what our current logic can sustain. We are staring into a gap in the fabric of the cosmos, and for the first time, we are beginning to suspect that the gap may not be fillable. Devony, dark sector, encroachment. We are beginning to realize that the matter we can see is merely a dusting of soot on a much larger, darker structure that does not obey the light. You look at the night sky and see the stars, the nebulae, and the glowing bands of galaxies, and you assume you are seeing the universe. But the photons hitting your retina are reporting on only 5% of what is actually there. The atoms that compose your body, the oxygen you breathe, and the silicon in your devices are an anomaly, a rare, luminous impurity in a cosmos dominated by a dark sector that remains utterly indifferent to the electromagnetic force. This is not a theory about a distant place. It is a description of the space you are currently occupying. As you sit in your chair, dark matter is streaming through you. It passes through your walls, your bones, and the very detectors we built to find it, without leaving a trace. We know it is there because we can measure its weight. We see galaxies spinning faster than they should, held together by the gravitational grip of an invisible mass that outweighs visible matter 5 to 1. At the Large Hadron Collider, we have spent years attempting to produce dark particles by smashing protons together at nearly the speed of light. We expected to see energy disappear, to witness a collision where the conservation of momentum is violated because a piece of the wreckage has escaped into the dark sector. The unsettling reality is that we have found nothing. The dark sector has not blinked. This silence is a measurement in itself. It suggests that the dark world is not just a different kind of matter, but a different kind of reality entirely, one that may not share any of our fundamental forces except gravity. We are beginning to contemplate the dark sector encroachment, the possibility that there is a complex, invisible ecology existing in the same space as ours, completely decoupled from our perception. There could be dark atoms, dark chemistry, and dark structures occupying the room with you right now. And you would have no way of knowing, because the light that allows you to see the world does not touch them. This realization dismantles our assumption that we are the primary inhabitants of the universe. We are, instead, the 5%. We are the foam on the surface of a deep, dark ocean, whose properties we are only beginning to guess. The LHC was designed to be a bridge into this dark world, but the bridge has yet to find a shore. This lack of interaction suggests a portal problem. If the dark sector only interacts through gravity, the weakest of all forces, then the barrier between our world and theirs is almost absolute. We are measuring a gravitational ghost that we can feel but never touch. Furthermore, the data from our most distant observations suggests that this dark structure is not static. Dark energy, the even more mysterious counterpart to dark matter, is actively pushing the universe apart, accelerating the expansion of space itself. It acts as a repulsive pressure inherent to the vacuum, ensuring that, eventually, every galaxy will be isolated in its own private horizon of darkness. The dark sector is not just a passive background, it is the engine of the future, and its ultimate goal appears to be the total dilution of everything we recognize as the world. You are an observer made of light-interacting matter, trying to understand a system that is fundamentally dark. We have reached a point in our measurements where the invisible is no longer a metaphor, but a calculated necessity. We are forced to accept that the majority of reality is composed of things that do not want to be seen. The encroachment of the dark sector into our scientific models is a reminder of our own marginality. We are a brief flash of light in a basement that has never known a sun, and we are just now realizing how large the basement truly is. 10. The measurement contradiction. When we look at the expansion of space, the numbers we get from the early universe do not match the numbers we get from the modern one, and the gap is growing. You are accustomed to the idea that a physical fact, like the rate at which a car is moving or the height of a mountain, is a singular, objective truth. If two different, high-precision instruments measure the same thing and get two different results, you assume one of them is broken. But in the study of the cosmos, we are currently using our most advanced clocks to measure the expansion of the universe, and they are refusing to agree. This is the Hubble tension, and it suggests that the very fabric of time and distance may be behaving in a way that our current physics cannot describe. On one hand, we have the early universe measurement. By looking at the cosmic microwave background, the afterglow of the Big Bang,
we can calculate exactly how fast the universe was expanding when it was just a few 100,000 years old.
When we project that data forward, using our best mathematical models, we get a specific value for the expansion rate today, known as the Hubble constant. On the other hand, we have the local measurement. We look at the stars in our own neighborhood, Type 1 a supernovae and Cepheid variables, and measure how fast they are actually receding from us right now. These two methods are not just slightly off, they are in direct, statistically significant conflict. The universe is expanding faster than it is allowed to. This is not a matter of human error. The precision of these measurements has reached a point where the error bars no longer overlap. It is as if you measured your own height with a ruler and found you were 6 feet tall, but your shadow, measured by the physics of light, insisted you were 7 feet tall. Both measurements are technically perfect, yet they describe two different realities. This contradiction implies that there is a fundamental dark ingredient missing from our cosmic recipe. Perhaps a new form of energy that acted in the early universe, or a property of space that causes it to stretch more violently than gravity should allow. At the Large Hadron Collider, we look for the small-scale version of this conflict. We look for discrepancies in how particles behave compared to how they should behave according to the standard model. What we are finding is a parallel tension. Just as the universe expands faster than our models predict, certain subatomic processes occur with an inexplicable frequency. We are seeing a pattern of mismatch that spans the entire scale of existence, from the smallest quark to the largest galaxy filament. The common thread is that our math is too slow, too rigid, to account for the actual vitality of the vacuum. You must confront the possibility that the laws of physics are not constant across time. If the expansion rate can change in ways our models don't account for, then the relationship between distance and time is not a fixed bridge. It is a shifting, organic thing. We are trying to navigate a landscape where the map is drawn in a different language than the terrain. This measurement contradiction is a warning that our understanding of causality is localized. We have assumed that the rules we find here, in our small corner of the present, can be exported to the beginning of time. The data is telling us that we are wrong. The gap between these two numbers is not a failure of technology. It is a discovery of a limit. We have reached the edge of what the standard model of cosmology can explain. We are staring at a rift in our data that represents a rift in reality itself. If the early universe and the late universe cannot be reconciled, then the story we tell ourselves about the history of space is a fiction, a convenient narrative that is now being dismantled by the very precision we used to construct it. We are measuring a world that is pulling itself apart faster than we can understand why. 11. The persistence of the impossible. You assume that a contradiction in science leads to a quick correction, but we are entering an era where the data is perfect and the conclusions are impossible. In the past, when a measurement deviated from a theory, we looked for a smudge on the lens or a loose cable in the detector. We assumed the error was ours, not the universe's. But at the Large Hadron Collider, and across the breadth of modern observational astronomy, we have reached a plateau of technical excellence where the errors have been stripped away, leaving only the raw, naked paradox. We are no longer looking at noise in the system. We are looking at a signal that tells us our fundamental logic is incompatible with the world it attempts to describe. This is the persistence of the impossible, a state where the more we refine our instruments, the more the contradiction solidifies. You believe that reality must be internally consistent, that A cannot also be B. Yet our most successful theory, quantum mechanics, demands that we accept exactly that. We see particles that exist as waves of probability until the moment they are observed, and we see entangled pairs that communicate across light years instantaneously. We have moved past the point of weirdness and into a regime where the data is telling us that our basic assumptions about locality, causality, and time are not just incomplete, they are false. Consider the anomaly. In several independent experiments at CERN, we have observed particles behaving in ways that simply cannot happen if the standard model is a complete description of nature. We see decays that violate the laws of energy conservation in the short term, and we see interactions that suggest the existence of forces for which we have no name. In a previous era, these would be dismissed as anomalies to be smoothed over. Today, they persist through every upgrade, every calibration, and every statistical check. They are not going away. The impossible is becoming a permanent fixture of our datasets. This creates a psychological rift in the scientific community. We continue to use the old formulas because they work for building bridges and launching satellites. But we know with mathematical certainty that they fail at the foundation. You are living in a world that is functionally real, but fundamentally impossible. We are like sailors who have discovered that the ocean is made of a substance that shouldn't be liquid, yet we continue to sail upon it because we have no other choice. The persistence of these impossible measurements suggests that we are not living in the base reality, but in a localized projection where the rules are merely approximations. Every time the LHC records a collision that defies the expected symmetry, it is a reminder that our logic is a closed loop. We are looking for answers using a system of thought that may be the very thing preventing us from seeing the truth. If the data is perfect and the conclusion is impossible, then the impossible is simply a fact that our current paradigm cannot digest. We are accumulating a mountain of facts that we cannot explain, and the weight of that mountain is starting to crush the theories that built it. We are not waiting for a new discovery. We are waiting for a new way to think. You are witnessing the end of the era of easy physics. We have picked the low-hanging fruit of the observable world, and what remains are the structural contradictions that mock our sense of order. The persistence of the impossible is the ultimate check on human ego. It suggests that the universe is not only stranger than we imagine, but stranger than we can imagine. We are measuring the boundaries of a reality that does not care if it makes sense to you. It simply is. And the data is the only truth we have left, even if that truth tells us that nothing we believe is actually true. 12. The vacuum decay scenario. The vacuum decay scenario. The stability of your world depends on the vacuum being at its lowest possible energy state. But current measurements suggest we are perched on a ledge. You assume that the void of space is a final, settled thing, the ultimate basement of reality. But in the language of quantum field theory, a vacuum is not an absence, but a state of energy. Just as water can exist as a liquid, even when it is cooled below its freezing point, a state known as supercooling, the vacuum of our universe may be metastable. We are living in a false vacuum, a temporary plateau in the energy landscape. This is not a speculative dread. It is a direct implication of the mass of the Higgs boson measured at the Large Hadron Collider. If the Higgs field were in its true vacuum, its absolute lowest energy state, the laws of physics would be locked in place forever. But the data from CERN suggests that the Higgs field is not at the bottom of the valley. It is sitting in a shallow dip on the side of a mountain. Beyond the ridge of this dip lies a much deeper valley, the true vacuum. To reach it, the field would need to overcome a massive energy barrier. Under the rules of classical physics, this would be impossible. But you live in a quantum universe, where particles and fields do not need to climb over barriers. They can tunnel through them. At any moment, in any coordinate of space, a piece of the Higgs field could quantum tunnel into the lower state. This would trigger a phase transition, the vacuum decay. It would begin as a microscopic bubble of the true vacuum, a sphere of new physics. Inside this bubble, the laws of nature would be fundamentally different. The mass of particles would change, or mass might vanish entirely. The forces that hold your atoms together would cease to function. This bubble would expand at the speed of light, driven by the enormous energy difference between the two states. Because it moves at the speed of light, you would have no warning. There is no signal that can outrun it. The sky would not turn red. The stars would not flicker. One moment you are sitting in your room, and the next, the very concept of a room or a body is overwritten by a more stable but entirely uninhabitable reality. The measurement of the Higgs mass at 125 giga-electron volts places us in a terrifyingly specific region of the mathematical map. It is the region of marginal stability. If the Higgs were just a few percent heavier, the vacuum would be absolutely stable, and the universe would be safe for eternity. If it were lighter, the vacuum would have already decayed in the heat of the Big Bang. Instead, we are in the middle. We are in a universe that is stable enough to last billions of years, but fragile enough to end in an instant. We are measuring the expiration date of the cosmos, and the data suggests that the clock is ticking, even if the scale of that clock is trillions of years. This scenario redefines your relationship with the void. You often think of nothingness as a passive backdrop, but the vacuum decay scenario reveals that the vacuum is a latent force. It is a dormant predator. Every cubic centimeter of the space between your eyes and this screen is a pressurized container of potential change. We are observing the Higgs boson, not just as a piece of the puzzle, but as a thermometer, measuring the fever of the universe. The fact that the vacuum has not decayed yet is a statistical gift, but it is not a guarantee. We have built a machine to probe the limits of matter, and it has returned a measurement that suggests matter itself is a temporary phase. The impossible thing CERN found is the precision of our own precariousness. We are looking at the fundamental constants and seeing not a solid foundation, but a precarious balance. The vacuum is not empty, it is waiting. And as we continue to push particles to higher and higher energies, we are forced to ask if we are merely observing this instability, or if, in our search for the ultimate truth, we are tapping on the glass of the very barrier that keeps the vacuum from collapsing. 13. False vacuum realities. If the universe is in a false state, then the laws of physics as you know them are temporary, a localized glitch in a much larger, more hostile system. You tend to view the constants of nature as eternal truths carved into the bedrock of existence. You assume that an electron will always have the same charge, and that gravity will always pull with the same relentless hand.
But if we are residing in a false vacuum, these laws are merely the weather of our current epoch. They are the result of the Higgs field being caught in a specific high-energy configuration. In a true vacuum, the state the universe wants to be in, the forces of nature would be unrecognizable. We are living inside a bubble of instability, a transient phase in a cosmic history that is far more indifferent to life than we dared to imagine. The concept of a false vacuum implies that our reality is a state of supercooling on a cosmological scale. Just as liquid water can remain liquid below its freezing point until a single seed crystal triggers a flash freeze, the universe is currently liquid when it should be solid. We are suspended in a high-energy phase because the transition to the lower state is statistically unlikely to happen all at once. This means that the vacuum you perceive as a void is actually a pressurized medium, held back by a quantum barrier. The measurements at the Large Hadron Collider have confirmed that the Higgs boson sits right on the edge of this transition zone. We are not in the basement. We are in a room on the second floor, and the floorboards are beginning to groan. This realization changes the meaning of the word natural. If the physics of our universe is a localized glitch, then the vast majority of the greater universe may be fundamentally hostile to the existence of matter. In a true vacuum state, the Higgs field would settle into a much deeper minimum, potentially making particles so heavy they immediately collapse, or so light they can never form structures. Our false vacuum reality is a tiny, improbable oasis where the values happened to fall within the narrow range required for atoms to bond. We are not the standard. We are the exception. We are a brief deviation from a much colder, more chaotic norm. Consider the implications for the future of observation. If the laws of physics are temporary, then our current science is a study of a passing shadow. We are documenting the properties of a bubble that is destined to burst. This metastability suggests that the universe has a built-in reset button. This is not a slow heat death or a gradual fading of the stars, but a sharp, instantaneous rewrite of the cosmic code. The data from CERN suggests that the probability of this happening is low in the next few billion years. But in the infinite timeline of the cosmos, low probability is a certainty. We are measuring the duration of a miracle that we now know has an end. You must also confront the possibility that other regions of space-time have already transitioned. If the universe is infinite, then somewhere, beyond our light horizon, the vacuum may have already decayed. There could be true vacuum bubbles expanding through the abyss right now, erasing entire galaxies and replacing them with a different set of physical laws. In those regions, there are no stars, no light, and no observers. There is only the true vacuum, the final, settled state of the field. We are in a race against a horizon of non-existence that we cannot see and cannot stop. We have spent centuries trying to find the universal laws, believing they were the ultimate objective truth. But the impossible thing we have found is that these laws are context-dependent. They are the properties of our specific false state. The Large Hadron Collider has pulled back the curtain on a reality that is far more fragile and far more alien than we suspected. We are inhabitants of a false reality, observing the signs of our own obsolescence through the very particles that allow us to exist. The stability you feel is a statistical illusion, a temporary stay of execution in a universe that is eventually going to return to its true,
empty self. 14. The bubble of nothingness. At any moment, a transition could begin at a single point in space, a ripple of true vacuum that would rewrite the properties of matter at the speed of light. You have been raised to believe that the end of the world would be an event, a slow progression of heat death, a stellar collapse, or a geological upheaval. But the physics of the vacuum suggests something far more clinical. This is the nucleation of a true vacuum bubble. It does not require a grand cosmic collision. It only requires a single quantum fluctuation, a microscopic accident, where the Higgs field tunnels through its current energy barrier. In that instant, a sphere of new reality is born, and it possesses a surface tension of unimaginable proportions. As this bubble expands, it does not push matter aside, it consumes it. The shell of the bubble, traveling at the speed of light, represents a phase transition of the laws of physics themselves. Behind this wall, the fundamental constants are different. The way the weak nuclear force couples with matter is altered. The electromagnetic field, which governs the light you see and the electricity in your brain, is restructured. As the wall of the bubble passes through you, the atoms in your body would not explode. They would simply cease to be defined as atoms. The chemical bonds holding your DNA together would vanish because the particles involved no longer recognize the instructions of the previous reality. You must understand that because this front moves at c, the universal speed limit, there is no causal way to perceive its approach. No telescope can see it coming, because the light from the destruction arrives at the exact same moment as the destruction itself. 1 millisecond, the universe is a place of stars and chemistry. The next, it is a volume of space where the vacuum energy has dropped to its absolute minimum, rendering the existence of complex matter impossible. It is the ultimate nothingness, not a vacuum in the way we currently understand it, but a state of being so stable and so low energy that it leaves no room for the excitations we call particles. This is the silent predator of the cosmos. We have measured the stability of the Higgs field at CERN and found that the universe is metastable, which is the scientific term for temporary. We are living in a house of cards that has remained standing for 13.8 billion years, giving us the false impression of permanence. But in the infinite timeline of a quantum universe, every possible event must eventually occur. The nucleation of a bubble of nothingness is a statistical certainty. We are simply existing in the window before the first event reaches our coordinates. The Large Hadron Collider has not created this danger, but it has confirmed that the danger is a structural component of the space you inhabit. Inside the bubble, the universe is at peace. It has reached the state it has been trying to achieve since the Big Bang, the global minimum of energy. The turbulence of the false state, which allows for the existence of stars, planets, and observers, is finally stilled. To the universe, we are a high-energy impurity that needs to be filtered out. The bubble of nothingness is the universe's way of returning to equilibrium. We are measuring the edge of this potentiality, realizing that our entire history, every civilization, every memory, every thought, is contained within a pocket of space that is fundamentally wrong. We are now faced with the realization that the vacuum is not a passive stage, but a volatile substance. We are trying to understand the impossible measurement of the Higgs mass, only to find that its value is the exact number required to keep us on the brink of this collapse. We are looking at the clock of the cosmos, and for the first time, we are seeing the hands move towards zero. The bubble of nothingness is the ultimate resolution of the paradoxes we have found, a final, silent answer to the contradictions of a reality that was never meant to last. 15. The illusion of locality. We have observed particles that remain connected across vast distances, suggesting that space is not a separator, but a secondary projection of something else. You rely on the concept of distance to maintain your sense of order. You believe that for one object to affect another, there must be a physical mediation, a touch, a wave, or a signal traveling through the intervening gap. This is the principle of locality, the foundation of classical physics and your daily intuition. But the measurements coming out of high-energy physics and quantum optics have demonstrated that, at a fundamental level, distance is an illusion. We have measured entangled particles, where a change to one is reflected in the other instantaneously, regardless of whether they are separated by centimeters or light years. This phenomenon, which Einstein famously dismissed as spooky action at a distance, has been verified with a precision that leaves no room for doubt. It implies that the three-dimensional space you move through is not the base layer of reality. If two objects can remain perfectly synchronized without any signal passing between them, it suggests that they are not truly separate entities. They are, instead, two different points of contact for a single, underlying structure that exists outside of our conventional dimensions. You are seeing the tips of two fingers on the same hand, mistakenly believing them to be independent actors because the hand itself is invisible to your instruments. At the Large Hadron Collider, the study of particle interactions increasingly points toward a universe that is non-local. When we collide protons, the resulting spray of debris is not just a random collection of parts. It is a system governed by correlations that defy the speed of light. We are beginning to realize that space may be an emergent property, much like the temperature of a gas is an emergent property of moving molecules. If space is not fundamental, then the vast distances between galaxies and the small distances between the atoms in your hand are not real barriers. They are a specific way of organizing information, a user interface that allows us to navigate a reality that is actually interconnected in ways we cannot visualize. This has unsettling implications for our understanding of causality. If locality is an illusion, then the idea that here is different from there is a persistent error of perception. It means that every point in the universe is, in some sense, connected to every other point. The reason you cannot walk through a wall or teleport to a distant star is not because the universe forbids it, but because the code of our current vacuum state enforces a strict set of rules about how information is allowed to move. We are measuring the constraints of the projection, not the limits of the source. The Large Hadron Collider is essentially an instrument designed to stress test this projection. By concentrating enormous amounts of energy into a microscopic point, we are trying to see if the interface glitches. What we find are the impossible correlations that break reality as we know it. We find that the more we look for the solid, localized building blocks of matter, the more they dissolve into a web of non-local relationships. You are not a collection of separate particles located in a room. You are a localized excitation of a field that spans the entire cosmos, inextricably linked to the furthest edges of the observable universe. We are forced to consider the holographic principle, the idea that the three-dimensional volume of the universe is actually a projection of information stored on a two-dimensional boundary. If this is true, then the depth and distance you perceive are mathematical artifacts,
no more real than the depth you see on a cinema screen. The impossible measurements we are recording are the first signs of the pixels at the edge of the display. We are discovering that the architecture of space is a secondary effect, and that beneath the illusion of locality, there is a singular, unified system that does not recognize the concept of away. 16. The holographic constraint. There is a limit to how much information a volume of space can hold, a limit that suggests the third dimension is an emergent property rather than a fundamental one. You perceive the room around you as a vast container, a three-dimensional stage with a specific depth, height, and width. You assume that if you wanted to store more information within that room, more atoms, more data, more complexity, you would simply need to fill the volume. But the laws of black hole thermodynamics and the recent high-energy data from the Large Hadron Collider suggest a different, more restrictive reality. The total information capacity of any region of space is not determined by its volume, but by its surface area. This is the Bekenstein-Hawking bound, and it implies that the third dimension may be an elaborate mathematical facade. To understand the implications, imagine a computer chip. To increase its power, you want to pack as many transistors as possible into its three-dimensional structure. However, in our universe, if you attempt to pack too much information into a specific volume, the energy density becomes so great that the region collapses into a black hole. At that point, the information is no longer distributed throughout the center. It is smeared across the two-dimensional surface event horizon. This is the holographic constraint. It suggests that the bits of reality, the fundamental descriptions of every particle and force, are actually written on a flat, distant boundary, and the world you inhabit is the projection cast by that data. This is not a metaphorical comparison. In the quest to unify gravity with quantum mechanics, the holographic principle has become one of our most mathematically robust tools. When we collide particles at CERN, we are effectively probing the resolution of this projection. We are looking for the point where the 3D illusion begins to pixelate. If the third dimension were truly fundamental, we should be able to probe smaller and smaller volumes of space indefinitely. But if the holographic model is correct, there is a fundamental graininess to space-time, a limit dictated by the Planck scale, beyond which the concept of position in 3 dimensions ceases to exist. We are measuring a reality that has a maximum bandwidth, and we are starting to see the flicker in the frame rate. The discomfort lies in what this says about your own physicality. If your body is a 3-dimensional representation of 2-dimensional data, then your sense of internal reality is a secondary effect. Your organs, your blood, and the neurons firing in your brain are not inside you in the way you think. They are the rendered output of information stored elsewhere. This changes the nature of the impossible measurements at the LHC. We are not finding new particles, so much as we are finding new ways that the underlying 2D code is being processed. The hierarchy problem and the vacuum decay are not errors in the world. They are errors in our interpretation of the projection. We have been trying to solve a 2D puzzle by looking only at the 3D shadows it casts. As our detectors become more precise, we are encountering the holographic noise, the minute quantum fluctuations that occur when you try to measure a volume that is nearing its informational limit. It is as if we are zooming in on a high-definition photograph until the individual dots of ink become visible. At this level, the distinction between here and there vanishes. The geometry of the small is revealed to be a flat map
folded in a way that creates the illusion of depth. The third dimension is a convenient shorthand the universe uses to organize its data, a way to keep information from overlapping. But it is not a place that actually exists. We are forced to confront a measurement of reality that is internally consistent only if we abandon the idea of volume. The holographic constraint is a ceiling on human understanding, a reminder that we are inhabitants of a surface we cannot see, experiencing a depth that isn't there. We have built our physics on the assumption that the world is a box, but the data is telling us that the box is just a screen. The impossible findings at CERN are the artifacts of the projection, the strange distortions that occur when the three-dimensional rendering attempts to account for the two-dimensional truth. 17. The entropy of information. Every time a particle interacts, it creates a record, and the total amount of information in the universe is a debt that must eventually be paid. You think of information as something digital or abstract, the words on this screen, the memories in your mind, or the data stored in a cloud. But in fundamental physics, information is a physical property, as real as mass or charge. It is the measure of how a system is organized. When two particles collide in the tunnels of the Large Hadron Collider, they do not just exchange energy, they exchange state. They know about each other. This exchange is indelible. Even if those particles fly to opposite ends of the galaxy, the universe must maintain the record of that interaction to preserve the laws of causality. This record is entropy, and it is the hidden accounting system of reality. The second law of thermodynamics states that the total entropy of an isolated system can never decrease, it can only grow. This means that the universe is constantly accumulating information, becoming more disordered and complex with every passing second. You see this as the arrow of time. You can break an egg, but you cannot unbreak it, because the universe has already written the record of the breakage into the fabric of space-time. To reverse the event would require the erasure of information, and the universe does not have an undo function. Every breath you take, every chemical reaction in your cells, and every star that burns out contributes to this growing debt. We are living in a system that is slowly being choked by its own history. The crisis we face at the limits of measurement is the realization that information has a physical cost. This is known as Landauer's principle. The erasure of one bit of information releases a specific amount of heat into the environment. If the universe were to continue forever, it would eventually reach a state of maximum entropy, a heat death, where all information is so thoroughly distributed that no work can be performed and no structures can exist. But the data from the LHC suggests something more immediate and unsettling. We are seeing that, at extremely high energy densities, the cost of maintaining information begins to warp the geometry of space itself. When we pack too much information into too small a space, the universe's accounting system fails. This is what happens at the event horizon of a black hole. It is a point where the informational density reaches the Bekenstein-Hawking limit, and the three-dimensional record is forced onto a two-dimensional surface. We are beginning to realize that the impossible measurements we record, the anomalies in particle decays, and the strange stability of the vacuum, may be the result of the universe trying to manage an informational overflow. We are reaching the capacity of our local sector of space-time to record new events. Consider the information paradox. If a particle falls into a black hole, its information appears to be lost to the outside world, which would violate the fundamental principle of unitarity, the rule that information can never be destroyed. Physicists have spent decades trying to reconcile this. The current consensus is that the information is not lost, but scrambled beyond recognition, encoded in the Hawking radiation that the black hole eventually emits. This implies that the universe is an obsessive archivist, refusing to let go of a single bit of data, even if it means tearing the fabric of reality to store it. You are a complex, localized peak of information. Your body is a highly ordered arrangement of atoms that requires a massive informational tax to maintain. Every second you exist, you are pushing against the rising tide of entropy, creating a trail of disordered energy in your wake. The impossible findings at CERN suggest that we are approaching a limit where the universe can no longer balance the books. We are measuring the friction of existence. We have found that the universe is not just a collection of matter and energy, but a finite ledger of data. And we are rapidly approaching the final page. 18. The non-existence of time. In the equations that describe the fundamental state of the universe, the variable for time often disappears, leaving us with a static, frozen block of events. You perceive time as a river, a relentless flow from a definite past toward an uncertain future. This now you inhabit feels uniquely real, a thin edge of existence moving through a void of what has been and what is yet to be. But when we look at the core of our most advanced physics, specifically the Wheeler-DeWitt equation, which attempts to combine quantum mechanics with general relativity, the T for time simply vanishes. The math describes a universe that does not happen. It simply is. This is the block universe theory, and it suggests that your sense of passage is a cognitive illusion, a byproduct of how your brain processes a static, four-dimensional geometry. If you could step outside the 3 dimensions of space and the 4th dimension of time, you would see the universe not as a sequence of events, but as a giant, unchanging sculpture. Your birth, your present moment, and your eventual death are all equally present within this structure. They are coordinates, no different from left or right or up. The reason you feel time moving forward is not because the universe is changing, but because of the way entropy increases along a specific direction of this block. Your consciousness is like a needle on a record player, reading the grooves of a disc that has already been pressed. The music is all there at once. You are merely experiencing it one note at a time. At the Large Hadron Collider, we are forced to confront this frozen reality when we measure the behavior of particles at the quantum level. In the high-energy collisions of protons, we see processes that appear to be time-symmetric. On a fundamental level, most laws of physics work exactly the same way, whether time runs forward or backward. A particle decaying into 2 smaller ones looks identical to 2 smaller particles merging into one if the film is reversed. This indifference to the arrow of time suggests that the arrow is not a fundamental law of the universe, but an emergent property of large-scale systems. The deeper we go into the subatomic world, the more the distinction between before and after dissolves into a haze of simultaneous possibilities. This leads us to the problem of time in quantum cosmology. If the universe is a static block, how does change occur? Why do you remember the past but not the future?
The answer lies in the impossible measurements of the vacuum itself. We have found that the universe is governed by a series of correlations that link different parts of the space-time block together. These correlations create a path that your brain interprets as a chronological sequence. But the path is already laid out. We are discovering that the future is just as determined by the geometry of the block as the past is. This is the ultimate form of determinism, a reality where nothing is ever truly new, and where every event is a permanent, indelible part of the cosmic architecture. The discomfort of this realization is profound. It implies that choice is a narrative you construct to explain your movement along a predetermined coordinate. We are measuring the specific slices of the block universe at CERN, looking for evidence of how these slices are stitched together. What we find is that the seams are invisible. There is no moment of transition between one state and the next, only a continuous, four-dimensional manifold. The impossible thing we are measuring is the lack of a clock at the center of the world. The universe does not keep time. It has no need for it. You are a segment of a four-dimensional worm, a structure extending from your first breath to your last. You cannot see the whole of yourself because your perception is trapped in a three-dimensional cross-section. But the math does not lie. The time you think you are losing is still there, just as the city you left behind on a journey still exists even when you are no longer in its streets. We have reached a point in our measurements where we must accept that our most intimate experience, the passage of time, is a structural misunderstanding of the reality we occupy. The universe is a finished book, and we are simply the characters discovering the words on the page we are currently inhabiting. 19. The observer effect. You believe you are a passive witness to reality, but the act of measurement forces the universe to choose a state, implying a terrifying link between mind and matter. You assume that the world exists independently of your gaze, that the moon is there even when no one is looking, and that a particle has a definite position whether or not it is detected. But the data gathered from nearly a century of quantum experiments, culminating in the ultra-precise measurements at the Large Hadron Collider, tells a much more disturbing story. At the fundamental level, matter does not exist as a collection of things, but as a cloud of possibilities. It is the act of observation that collapses this cloud into a single, localized fact. Without the measurement, the universe remains a blurry, superimposed ghost of itself. In your daily life, you interact with the macroscopic world, where objects seem solid and fixed. But this solidity is a collective illusion born of billions of observations happening every nanosecond. When we isolate a single particle in the vacuum of the LHC and attempt to determine its properties, we find that it does not possess them until we ask it to. Before the measurement, a particle can be in two places at once, or spin in two opposite directions simultaneously. This is not a failure of our technology. It is a fundamental property of the vacuum. The universe is a participatory system. It requires an witness to settle into a concrete reality. This is the observer effect, and it suggests that the line between the inner world of your perception and the outer world of objective fact is non-existent. The implications of this are often sanitized in popular science, but the raw data is unsettling. If the universe requires an observer to manifest its properties, then what happened during the billions of years before life emerged? Does the past only exist because we are looking at its remnants now? Some interpretations of the impossible data suggest that we are collapsing the history of the universe in reverse. By measuring the cosmic microwave background, or the Higgs field today, we are forcing the early universe to have had a specific state. This delayed choice effect has been demonstrated in laboratory settings. A measurement made in the present can determine the path a particle took in the past. We are not just watching the story. We are, through the mere act of looking, writing the script as we go. At CERN, we are the most active observers in history. We are bombarding the vacuum with questions, forcing it to choose states that it would never naturally occupy. We are searching for the God particle, but we may be finding that the God in the equation is the observer themselves. This creates a terrifying feedback loop. If our measurements influence the state of the vacuum, then our pursuit of knowledge is not a neutral act. We are poking at the foundation of reality, and the reality is responding to our curiosity by hardening into the shapes we expect to see. We must ask if we are discovering the laws of physics, or if we are accidentally inventing them through the intensity of our gaze. Consider the quantum Zeno effect, where a system that is observed continuously can never change. By looking at a particle, we freeze it in time. This suggests that the very flow of events, the happening of the world, is tied to the frequency and nature of observation. You are not a spectator in a theater. You are a sensor in a vast, self-sensing machine. Your consciousness is the mechanism by which the universe resolves its own mathematical uncertainties. Without you, or something like you, the universe would return to a state of pure, unmanifested potential, a vast nothingness that is simultaneously everything. We have reached the point in our measurements where the data can no longer be separated from the detector. The impossible results at the LHC are a reminder that there is no out there. The universe is a mirror, and the strange, broken symmetries we see in the subatomic world may be a reflection of the limitations of our own biological and mechanical senses. We are measuring the link between mind and matter and finding that the link is not a bridge, but a knot. The more we try to untie it, the more we realize that we are the ones holding the strings. 20. The limits of logic. The limits of logic. We are using a brain evolved for survival on a savanna to interpret the vibrations of 11-dimensional strings, and the friction is starting to show. You assume that your mind is a universal key, capable of unlocking any door in the cosmos if given enough time and data. But your cognitive architecture was designed for a middle-world existence, a realm of medium-sized objects moving at slow speeds, where cause and effect are linear and immediate. Your intuition is a tool for navigating 3 dimensions of space and 1 of time. When we use the Large Hadron Collider to push beyond these boundaries, we are forcing our neural pathways to process information that they were never meant to contain. We are attempting to describe the infinite and the infinitesimal using a language built for hunting and gathering. This friction manifests as the impossible results we are now recording. We find that, at the subatomic scale, a thing can be both a particle and a wave. We find that the vacuum has energy, but no mass. We find that time does not exist in the fundamental equations. To your brain, these are paradoxes, logical errors that must be resolved. But to the universe, they are simply facts. The contradiction lies not in the world, but in the interface between the world and your perception. We are reaching the cognitive horizon of our species. Just as a dog can never understand the concept of a prime number, despite living in a world governed by them, there may be structural truths about reality that are simply inaccessible to human logic. This is the ultimate limitation of our scientific models. We use mathematics as a proxy for understanding, but math is a human invention, a formalization of our own logical patterns. When the math begins to yield infinities or singularities, as it does in the center of a black hole or at the moment of the Big Bang, it is the universe telling us that our system of thought has reached its breaking point. At CERN, we are increasingly reliant on effective field theories, which are essentially mathematical patches used to ignore the parts of reality that don't make sense. We are building a map of a territory that we can no longer fully visualize, using symbols to represent concepts that our brains find repulsive. Consider the concept of quantum non-locality. Your brain insists that for something to move from point A to point B, it must travel through the space in between. But the data shows that this is not always true. This impossible movement is only impossible if you insist on the logic of the savannah. If you accept that space is a secondary projection, the mystery vanishes, but your ability to intuitively understand the world vanishes with it. We are entering an era of black box science, where we can predict the behavior of particles with perfect accuracy. Yet, we have no idea why the rules are what they are. We have the data, but we have lost the narrative. The impossible findings at the LHC are the first signals that we are hitting the ceiling of our biological capacity. We are discovering that the universe is not just stranger than we imagine, but stranger than we can imagine. Our logic is a local adaptation, a set of rules that worked well enough to keep our ancestors alive, but it was never intended to be a manual for the cosmos. We are measuring the vibrations of a reality that is fundamentally alien to the human mind. The friction we feel is the sound of our own mental gears grinding against a truth that is too large, too complex, and too indifferent to fit within our skulls. We are left with a choice. Do we trust our logic, or do we trust the data? If we trust the logic, then the universe is a broken, contradictory mess. If we trust the data, then our logic is a fragile, localized illusion. The Large Hadron Collider has not just found a particle, it has found the edge of the human mind. We are staring into a void where our words fail and our intuitions die, and we are beginning to realize that the truth may be something that we are simply not evolved to hear. 21. The cold silence of data. As we upgrade our detectors, we expect to find new particles, but instead, we find a haunting emptiness where our theories said there should be structure. You have been told that the history of science is a steady climb toward enlightenment, where every new tool reveals a new layer of reality. In the past, this was true. When we built better telescopes, we found new planets. When we built better microscopes, we found the cell. But at the Large Hadron Collider, the narrative has shifted. We have reached the highest energy levels ever achieved by human hands, peeling back the skin of the vacuum with terrifying precision. And we are finding that the universe is unexpectedly quiet. The new physics we were promised, the vibrant zoo of supersymmetrical partners and exotic matter, has failed to appear. This silence is not a failure of our technology, but a discovery in its own right. It is the null result that haunts modern physics. For decades, the best minds in the world predicted that just beyond the Higgs boson lay a treasure trove of new particles that would explain the nature of dark matter and the mystery of gravity. We called this naturalness. We assumed the universe would be natural and provide the answers we needed to balance our equations. Instead, the data is returning a flat line. We are measuring the vacuum at a resolution of 10 to the power of -19 meters, and we are finding that the standard model, a theory we know is incomplete, continues to work with a stubborn, inexplicable accuracy. This cold silence creates a crisis of expectation. If the particles we predicted do not exist, then the mathematical beauty we used to find them was a mirage. You must consider the possibility that we have been looking for the wrong thing entirely. We are like explorers who have reached the edge of the world and found not a new continent, but an endless, featureless sea. This emptiness suggests that the gaps in our knowledge, the dark matter, the hierarchy problem, the fine-tuning, cannot be solved by simply adding more stuff to the universe. The answer is not another particle. The answer may be a total rejection of the way we perceive reality. The data is clinical and cold. It does not offer the comfort of a new discovery. It offers the discomfort of a dead end. Every time the LHC completes a run and the statistical bumps disappear into the background noise, the silence grows louder. We are left with a universe that is mathematically impossible, yet physically present. This suggests that the ghost in the machine isn't a particle we can catch, but a fundamental flaw in our logic. We are measuring a reality that refuses to be explained by the rules we have written for it. We are staring into the abyss of the subatomic, and for the first time, the abyss is not staring back. It is simply empty. This silence has profound implications for the future of our species. If there is no new physics at these energy levels, then the dream of a theory of everything may be out of reach for centuries. We may have hit a desert, a vast range of energy scales where nothing new happens, stretching all the way to the Planck scale. If the universe is a desert, then we are isolated in a small oasis of understanding, surrounded by a void that we can never cross. The cold silence of data is the sound of a door closing. It is the universe telling us that we have reached the limit of what this particular path of inquiry can reveal. You are living in the era of the Great Silence. We have the most powerful machine ever built, and it is showing us that the universe is much more sparse and much more strange than we dared to imagine. The absence of evidence is becoming the evidence of absence, an absence of the order and symmetry we expected to find. We are left alone with the standard model, a lonely lighthouse in a dark, empty ocean. The impossible thing we have found is that the universe doesn't owe us an explanation. It is under no obligation to be natural or beautiful or even logical. It is simply there, and it is silent. 22. The cosmological constant problem. The disagreement between the predicted energy of the vacuum and the observed energy is the largest discrepancy in the history of science. You are used to scientific errors being matters of small percentages or decimal points, but this is a catastrophe of scale. When we use quantum field theory to calculate the energy inherent in empty space, the weight of the vacuum itself, the result is a number so vast it defies the vocabulary of mathematics.
Yet, when we look at the actual expansion of the universe, we see a value that is almost zero. The difference between our prediction and our observation is a factor of 112. To put that in perspective, if you were off by that much when measuring the width of a single atom, your result would be larger than the entire observable universe. This isn't just a small mistake. It is the most spectacular failure of human logic ever recorded. It implies that at the most fundamental level, we do not understand how gravity and the quantum world interact. According to the math, the vacuum should be so heavy with energy that the universe should have curled up into a microscopic ball or blown itself apart in the first trillionth of a second. But as you look around you, the stars are still there. The galaxies are drifting apart slowly, and the vacuum feels light. This suggests that there is a cancellation happening, a mechanism that wipes out 120 orders of magnitude of energy with perfect precision. At the Large Hadron Collider, we are searching for the source of this cancellation. We have looked for supersymmetry, which would provide a perfect mathematical balance, with superpartner particles canceling out the energy of the particles we know. But as we have seen, the detectors have remained silent. This leaves us with a terrifying alternative: anthropics. It suggests that there is no fundamental reason for the vacuum energy to be this low, other than the fact that if it were any higher, stars could never form, and you wouldn't be here to measure it. We are staring at a universe that seems to have been tuned to the edge of a knife, for reasons that may be beyond the scope of physics to explain. This discrepancy, often called the vacuum catastrophe, shatters our confidence in the predictive power of our models. If we can be wrong by 10,120 in our most successful theory, what else are we missing? It suggests that our understanding of nothingness is fundamentally flawed. We see the vacuum as a stage, but the math tells us it is a pressurized, energetic substance that is actively participating in the geometry of the cosmos. The impossible fact is that the vacuum energy is non-zero, yet almost zero. It is just enough to drive the acceleration of the universe, but not enough to destroy the possibility of complexity. We are measuring a ghost. Every cubic meter of space contains a tiny, persistent push, what we call dark energy, that corresponds to this cosmological constant. But we have no idea where it comes from or why it is so weak. It is as if we found a tidal wave that has been reduced to a gentle ripple for no discernible reason. We are looking for the filter that removed the energy, but the LHC shows us that the vacuum is exactly as we suspected: a turbulent quantum foam that should be heavy. The mismatch is not in the vacuum. The mismatch is in our reality. The cosmological constant problem is the ultimate keep out sign at the border of our understanding. It marks the point where quantum mechanics and general relativity refuse to speak the same language. Until we solve this discrepancy, our theory of everything is a house built on a foundation of 120 zeros. We are measuring the heartbeat of a universe that shouldn't exist, according to the very laws we used to discover it. 23. The fragility of the carbon bond. Your very existence is a mathematical outlier, a statistical impossibility that relies on a series of coincidences
we are now finding to be unstable. You think of yourself as solid, a permanent fixture of a material world. But the chemistry that allows life to function is a masterpiece of precision engineering performed on a collapsing stage. At the center of this drama is the carbon atom, the backbone of every protein, every strand of DNA, and every thought you have ever had. But the ability of carbon to form these complex, stable chains is not a guaranteed law of nature. It is the result of a delicate resonance in the nuclear furnace of ancient stars. A balance that the Large Hadron Collider suggests is far more precarious than we once believed. To get carbon, 3 helium nuclei must collide almost simultaneously inside a star, a process known as the triple alpha process. The probability of this happening is nearly zero, except for a specific energy state discovered by Fred Hoyle, known as the Hoyle state. This state acts as a stepping stone, a perfect landing pad that allows the helium to fuse into carbon. If the strong nuclear force were different by less than 1%, this energy level would shift, carbon production would cease, and the universe would be a graveyard of hydrogen and helium. You are made of star stuff, but only because the fundamental constants of the universe are tuned to a specific frequency that allows carbon to exist in the first place. Once formed, the carbon bond itself is a miracle of electromagnetic balance. The way carbon shares electrons with oxygen, nitrogen, and hydrogen to build the double helix of your DNA requires the fine structure constant to be exactly what it is. At CERN, we are measuring the stability of these underlying fields. We are looking for drift in the constants, the possibility that the rules of chemistry are not fixed, but are slowly shifting as the universe expands. If the strength of electromagnetism were to fluctuate even slightly, the covalent bonds that hold your cells together would lose their grip. Your biology is not a static fact. It is a temporary equilibrium in a system that is constantly being buffeted by quantum fluctuations. This brings us to the fine-tuning of the organic world. We often talk about the Goldilocks zone for planets, the right distance from a sun. But we are discovering a Goldilocks zone for the laws of physics themselves. If the Higgs field were to shift into a different vacuum state, as discussed in the vacuum decay scenario, the mass of the electron would change. Even a marginal increase in electron mass would render the carbon-nitrogen bond unstable. The complex molecules of life would literally unzip, dissolving into a soup of simpler, non-functional elements. We are measuring the stiffness of these bonds at the subatomic level, and the results suggest that we are living in a narrow window of chemical possibility. The impossible realization here is that life is not the inevitable outcome of a stable universe. It is a lucky byproduct of a specific, perhaps temporary, arrangement of forces. We have long assumed that the laws of physics are the floor upon which the house of chemistry is built. But the data from the LHC suggests the floor is vibrating. The stability of the carbon bond is a consequence of the current energy level of the Higgs field, and as we have seen, that field is metastable. We are a carbon-based life form inhabiting a universe that may not be carbon-friendly forever. You are a biological consequence of a cosmic accident. Every time your heart beats, it is because a trillion carbon bonds are holding firm, governed by numbers that have no logical reason to be what they are. We are measuring the fragility of this arrangement, finding that the solid reality of your body is actually a high-wire act. The persistence of the carbon bond is the ultimate proof of our precariousness. We are a complex, beautiful glitch in a system that is fundamentally indifferent to the survival of the structures it creates. 24. The end of predictability. We are reaching the point where the math no longer provides answers, only descriptions of a reality that defies human comprehension. For centuries, the hallmark of a good theory was its ability to predict the future. We used Newton's laws to predict the return of Halley's comet, and Maxwell's equations to harness the invisible spectrum of radio waves. We believed that if we could just measure the initial conditions of the universe with enough precision, the entire tapestry of time would unfurl before us like a clockwork mechanism. But as we push the Large Hadron Collider to its absolute limits, that clockwork is shattering. We are finding that the deeper we go, the less the universe behaves like a machine, and the more it behaves like a chaotic, irreducible system, where the link between cause and effect is permanently severed. This is the transition from calculable physics to statistical surrender. In the quantum realm, we have replaced the certainties of classical motion with the wave function, a mathematical cloud of probabilities. We can no longer say where a particle is, we can only say where it is likely to be. While this works for building transistors and lasers, it represents a total collapse of predictability at the foundational level. At CERN, we are observing events that appear to happen for no reason at all. Particles pop into existence and vanish, or decay into pathways that defy every symmetrical law we have written. We are documenting a reality that is fundamentally lawless, governed not by rigid decrees, but by a rolling dice of cosmic chance. This loss of predictability is not a lack of data, it is a feature of the universe. The Heisenberg uncertainty principle dictates that there is a hard limit to what can be known. The more precisely we measure the position of a particle, the more its momentum becomes a blurred, unknowable mess. This is the universe's privacy policy. It refuses to allow us to see the full picture. We are measuring the impossible fact that the foundation of the world is built on a lack of information. We have reached a point where our math is merely a way of cataloging our ignorance, providing us with expected values for a world that refuses to be pinned down. Furthermore, we are encountering the chaos of the small. In classical systems, small changes lead to small effects. But at the energy scales of the LHC, the butterfly effect becomes a quantum nightmare. A single, infinitesimal fluctuation in the Higgs field could trigger a vacuum decay that erases the galaxy. We are realizing that the stability of our world is a statistical fluke, a temporary period of calm in a system that is inherently volatile. We can no longer predict how long this calm will last. We are measuring the half-life of reality itself, and the error bars are wide enough to swallow our entire civilization. This marks the end of the Enlightenment dream of a fully transparent universe. We once thought that the book of nature was written in the language of mathematics, and that we were the ones meant to read it. But the data is showing us that the book is written in a code that changes as you read it. The impossible results we record are the points where the math stops making sense, where we encounter singularities or infinities that tell us our logic has failed. We are no longer the masters of the machine. We are observers trapped inside a system that is becoming increasingly opaque. We have built the most complex instrument in human history, only to find that the most fundamental truth is unpredictable. The end of predictability is a humbling realization. It suggests that the order we see in the stars and the seasons
is a thin crust over a boiling ocean of quantum chaos. We are measuring the limits of our own foresight, finding that the universe is not a puzzle to be solved, but a mystery to be experienced. The data is perfect, the measurements are precise, but the conclusion is a silent admission that we no longer know what will happen next. 25. The final measurement. The final paradox. As the LHC begins its next high-luminosity run, we are not looking for a discovery. We are looking to see if the foundation of our world is even there. For decades, the goal was additive. We sought the next particle, the next force, the next chapter in a story of building blocks. But the data has led us to a subtractive realization. The more we zoom in, the more the concept of matter evaporates into fields. The fields dissolve into probabilities, and the probabilities point toward a reality that is non-local, holographic, and potentially temporary. We are no longer trying to find the God particle to complete the puzzle. We are testing the structural integrity of the puzzle itself, fearing that the impossible results we've gathered are not errors, but the sound of the universe's logic reaching its breaking point. This next era of physics is defined by the final paradox. The more precise our measurements become, the less real the world appears to be. By increasing the luminosity, the number of collisions occurring every second, we are effectively increasing the resolution of our cosmic microscope. We expect to see the fine details of the vacuum, but there is a growing suspicion among the scientific community that we might find nothing at all. Not a void, but a lack of causality. We are looking for new physics to save our theories of a stable, predictable universe. But the silence of the data suggests that the standard model might be a beautiful lie, a temporary approximation that holds only as long as we don't look too closely. If the high luminosity run fails to produce the expected supersymmetric particles or signs of dark matter, we face a crossroads. One path leads to the multiverse or anthropic explanation, the idea that our universe is just one of an infinite number of bubbles and its specific impossible laws are just a statistical fluke. In this scenario, there is no deeper why. We simply exist in the one version of reality that didn't collapse or explode. The other path is even more radical. It suggests that our mathematical description of the universe is fundamentally flawed because it assumes that the universe is an objective, external thing. The observer effect and the holographic constraint suggest that reality is a dialogue between information and consciousness, a projection that only crystallizes when it is measured. You must confront the possibility that the impossible results, the Hubble tension, the vacuum metastability, the non-existence of time, are not separate problems to be solved. They are the same problem. They are the symptoms of a world that is not made of stuff, but of relationships. We are trying to measure the weight of a shadow. The Large Hadron Collider is reaching the point where it is no longer probing particles, but the source code of the projection. And just like a program that begins to glitch when pushed beyond its intended parameters, our reality is showing signs of informational stress. The final paradox is that our search for the ultimate truth may be the very thing that destabilizes the illusion of a solid world. We are left standing at the edge of the known, looking into a dark ocean of data that refuses to conform to our expectations. We've built a monument to human reason in the form of a 27-kilometer ring of superconducting magnets. only to have that reason challenged by the very particles it was meant to capture. We are a species of observers trapped in a false vacuum, deciphering a holographic map of a frozen block universe, held together by the fragile resonance of a carbon bond. It is a terrifying, beautiful, and utterly impossible state of affairs. The next run of the LHC will not provide comfort. It will not return us to the simple world of Newton or Einstein. It will push us further into the impossible. We are measuring the end of the world as we knew it, and the beginning of a reality that we may never truly comprehend. The foundation may not be there, but we are still here, looking, measuring, and wondering. And, in a participatory universe, perhaps that act of wondering is the only thing keeping the lights on.